It's fabulous to see such a good audience here tonight for what will prove to be, I'm sure, a brilliant speaker. Hey, I've shared platforms with this gentleman, and the first rule is never follow him, always speak in advance. It's much better to be a warm-up act to Norman than to be the follow-up, because you'll just be dead. Okay, it's something of a tradition to have joint meetings between the Computer Conservation Society and Newcomen. We've had excellent talks in the past from Dr. Phil Judkins on Enigma. We had Liz Bruton talking on radio direction finding in the First World War. We've had a paper on the Ferranti Argus. So this continues in that tradition. Air Commodore Norman Bonnar was a natural candidate for this slot. I heard him speak 2 years ago in Doncaster. I've since heard him speak at Charterhouse and at the RAF Museum in Hendon earlier this year. He's a man of many parts, and it was a bit of a dilemma as to which topic to pick tonight, because as Norman will explain no doubt in passing, he was a nav radar in the V Bomber Force and has a truly remarkable account of his experiences flying Victors. Norman joined the RAF as a cadet in 1957 and trained as a navigator. He joined 15 Squadron, a Victor squadron, and flew both Victor Mark I and Mark II bombers as a navigator, and went on readiness at the time of the Cuba crisis in October 1962. In 1964, he transferred to the later Mark II Victors and was the first to fire a Blue Steel missile in the UK at Aberporth off the Welsh coast. He then worked on various things, on Phantom procurement, on Nimrod procurement, and went on to command RAF Waddington. He worked on Boeing AWACS E3s, and then went on to become Deputy Commander of NATO Early Warning Systems at Mons in Belgium. His career carried on. I believe you've just retired as a lecturer at University of Nottingham after 20 years service, is that right? And he's been President of the Royal Institute of Navigators. He's taught students, he's given papers throughout the UK to many professional groups. So without more ado, after a big build-up, Norman, it's all yours.
I'm wondering whether I should ask him to write my obituary. I hope you can hear me at the back. Okay, fine. Now, if you remember, longitude was a problem, and this dear old boy, John Harrison, eventually, after many years of effort, solved the problem with a clock. H4 in the bottom right-hand corner. You can go and see those at the Greenwich Observatory if you wish. They are still owned by the Navy, amazingly, not by the Greenwich Museum. However, guess what? Satellite navigation relies on time as well. It relies on clocks. This one being a typical rubidium clock that was launched a few years ago in the first prototype of the Galileo, which I'll explain later, navigation satellite. And they're also using hydrogen lasers, but time is what matters. The only reason this system works is because there's a very accurate, almost atomic standard clock in each satellite. Because this is a one-way system. Despite what people say about you're being tracked by GPS, garbage. This is a one-way system. If it was anything else, you wouldn't have the millions of users that you have. The one system that has tried to do that in China gave up. They produced a thing called BEDO 1, which was a transponder system. Inevitably, it limited the number of people who could use it, and they've given it up, and they've moved over to a similar system to GPS. In a minute. Some of the people at the back are perhaps too young to remember that. Sputnik, of course, was the first satellite. Now, what happened then was that a couple of lateral thinkers at a university in America, the Appledore Laboratories, listened to the frequency Doppler shift as those satellites, obviously low Earth orbit, traveling very fast, so big Doppler shift. They listened to it go over, and as a result of knowing where they were, obviously on the ground at a set place, they were able to predict the satellite's orbit. And they told the US Navy, they said, do you realise that if we knew the satellite's orbital parameters, we could actually give you a position on the ground. We could do it in reverse. Oh, said the Navy. So we ended up with the transit system, low Earth orbit. It went into use early on with the bombers. Our submarines used it as well, of course, initially. They still used Omega. That was the very low frequency, long range radar system, which was global, but very inaccurate. I used it in the air, and if you got 6 or 7 miles, you were lucky. But at least they could receive that 10 or 20 meters below the sea surface. To get transit, they had to stick an aerial up, and bombers don't like showing anything above the sea surface. Anyway, the transit project went ahead. It was very successful. It proved that the spacecraft worked well, was reliable. They proved also how better to predict the ephemeris orbits of these satellites. And as a result, it was released not only to the navies, but also to merchant marine. And the merchant mariners used it too. Now, it wasn't any use to aircraft, because aircraft were traveling too fast. You needed to be traveling relatively slowly to get good accuracy out of this thing. At the time, there were several other projects going on. US Navy were looking at timation, as they called it. The US Navy Observatory has responsibility, as the National Physical Laboratory has in this country, for the timing standards across America. And as a result, they are the people that put their inputs into the world time standard, Universal UTC. I'm sure you know what I mean by that. They were trying to put into orbit a clock that was good enough to be able to do their time transfers. At the same time, the US Air Force were testing a system for 3-dimensional navigation, and they were doing this at a ground range at Yuma, the Yuma Proving Ground. At the time, they were transmitting from the ground, and the aircraft was flying backwards and forwards above it to prove the concept that if they then put those transmitters into orbit and knew the orbital parameters, they would be able to produce a 3D system. Now, the Department of Defense said, hang on, you both can't do this, it's too much money, get together, sort out a common project, which they did. And it became the Navstar GPS project. The Navstar's been dropped these days, everybody just calls it GPS. And that project office formed in July of '73. This man, who I meet usually a couple of times a year, lovely guy, he's an honorary fellow of the Institute of Navigation. He was the head of that JPO for 6 years and saw the system into initial operational capability. He moved on to be an emeritus professor at Stanford University, and he's also the co-chairman of the United States Precision Navigation and Timing Advisory Board to the White House. So he's quite an important guy still. He can't believe what's happened to a project that he started as a false multiplier for the military. So they put their first Block 1, that was a prototype really, satellite into orbit in February of '78, and by December of that year they had all 4. And I remember flying in a Britannia, dear old aeroplane, over the North Pole with a postgraduate course in the Air Force, and we were able to time ourselves to be available, or to have all 4 satellites available, so that we got positioning as we approached the pole and came back down Greenland. And what is it? Well, everybody thinks the satellites, yes, but of course, there's a lot more than the 24 orbiting satellites, which, by the way, are in 6 orbital planes, perhaps a mistake. Europe and the Russians went for 3 orbital planes, but that's a story that will take a long time to explain. They're at 20,000 kilometers, medium Earth orbit, in other words, and they come around again every 12 hours. But the most important bits really are the control segment, the thing that keeps those satellites in the correct positions within the orbits, and also uploads to them the ephemeris data, the satellite orbital data that they need to transmit to you to get your little Garmin or whatever receiver you have to work. The user segment are those bits. Now, how does it work? Very briefly, how does it work? Each satellite in GPS case has a unique code. They call them the gold codes, and it's a code division multiple access system. So each satellite transmits a little code, and therefore you know which satellite you're listening to. The receiver receives and stores that ephemeris data that these satellites send at its rather slow rate at the moment, but I'll come back to that. And it compares it with the codes that it's got stored. It then measures the time of flight of those coded signals from 20,000 kilometers down to the receiver. And it calculates what we call a pseudo-range. Why do we call it pseudo-range? We call it that because there are some errors in there. The primary one is the clock in here. This is not a high-grade atomic clock. It's a bit of old quartz, like the thing on your wrist. And it therefore has that as an error. There's also a lot of atmospheric and other errors which I won't go into too much detail, but I'll talk about. So what does it do? Code correlates. Down comes this coded signal. The receiver replicates the signal and looks for the time of travel difference between the two, and as a result, a range. Now, obviously it's a spherical range, and if you've got 3 satellites, you can get a position, except for your clock error. So what do? We use 4 satellites. That gives you enough equations to get out latitude, longitude, height, and the correction to your clock. Now, we're in the space age, and we're in the Cold War, and all that went with it, so the Russians had to do something similar. I'm not going to try and say that, because I'm not a Russian speaker, but Glonass is what it stands for. And they launched their first 3 satellites in October of '82. They have a slightly different concept, 3 orbital planes, I said earlier, slightly higher inclination, because they wanted better visibility of the satellites in some of the northern regions, where if you're on the ground and behind a hill, obviously you get blocked from the view from the satellite. So they wanted a slightly higher inclination. Slightly lower orbital parameter, but still medium Earth orbit. But the main difference was each satellite transmits a different frequency. Well, it did when it started. Frequency division multiple access. They at the time, military. Soviet Union, we will have nothing to do with the International Telecommunications Union. Oh, what happened to the lights? Somebody turned it down. And so they wouldn't even listen to anybody who said, you're interfering with other people's use of these frequencies, this spectrum that, in the L-band. The result was that the radio astronomers got more and more upset. Now, until the Soviet Union collapsed and the Russian Federation took over as the main procurers of the system, they hadn't had any real intention of obeying ITU rules. The Russian Federation did, and when they went along and said in Geneva, we would like to become part of the world now, they were told, well, in which case you've got to give up a whole chunk of the frequency band you're using. The result now is that satellites either side of the Earth are actually transmitting on the same frequency. It works, but it means that you can't use it very well in space because you might see both, and they're not very good at sorting out if the same frequency is appearing when you're in space. GPS, of course, is used for positioning satellites. Now, a rather bad accident occurred. A Korean 747 managed, even with 3 men in the cockpit, mind you, they had given up the navigator, oh dear. The 2 pilots and the flight engineer punched in their latitude and longitudes of their waypoints into their 3 inertial navigation systems, and they got the latitude wrong in a couple of the waypoints. None of them noticed, and they strayed into Soviet airspace. At the time, there was a rivet-joined aircraft, American spy aircraft. We've just bought some, by the way. They're at Waddington. Well, not at the moment because the runway's dug up, but they were around. And they flew up against this 747 thinking it was a rivet joint and shot it down, and 250 passengers died. Reagan, as a result, said, when we get this system to work, we will make it available for civilian use. So the DoD said, yes, we'll do that. However, we are just a bit worried that this is rather accurate, 20, 30 meters. Somebody might use it against us. As a result, we'll wobble it a bit. So they introduced what they called selective availability. It wobbled the timing of the clocks slightly so that you got about 180 to 100 meters error. Still pretty good, good enough. But of course, civilians, including American civilians, including American state civilians, like the FAA, started looking at how they could get rid of this problem. That's a typical bit of wobble. Okay? How do you get rid of it? You go differential. You put a receiver on a known point on the ground, you measure the range details, information you're getting from the satellites, and work out some corrections, and the integrity data, is the satellite working properly, send it to a transmitter, and send it to the airplane. Selective availability didn't work. They kept it though. Now in August of '86, USAF took over control of what was then called Falcon Air Force Base, but they've actually since renamed it. It's near Colorado Springs. They renamed it Schreiber Air Force Base. Colonel Schreiber, or I think he was a general in the end, was the man who pushed forward the space program for the American Air Force and the American military in general. He was still alive. That was an unusual thing for them to do. Maybe if you look at American Air Force bases, they're named usually after people who already did. He was still alive when it happened. He's died since. But Schreiber, that was a breakthrough, really, for the Americans. Now, the good old ICAO said, we're going to accept that this is damn good. And sooner or later, we're going to adopt this as a primary system for air navigation for civil aircraft in the future. A few problems with that. We'll come back to that. Some receivers came out. These were military receivers built by Trimble and Rockwell Collins. One was using just the civilian signals, which are open and free for everybody to use. The other one was using encrypted signals, the P code as it's called, for the military. At the time, of course, that didn't involve selective availability at all, whereas the others were subject to it. The selective availability, however, as you see, disappears in a bit. So this plugger was slightly more accurate, not dramatically more accurate than an ordinary CA code receiver without selective availability, but it was more anti-jam resistant than the CA code. Now they put up their first Block II satellite, and I show this just to show the sort of size of these things, pretty damn big, in February of '89. That's the first production satellite. When they put up new satellites, they usually test them, most of these people usually test them for 5 or 6 months before they allow them to be used in the open world. They're that big because at the time, the odd Soviet test launch was going off with the odd 10 megaton burst in space. So they decided they've got to harden their satellites far more than you would think of doing today. It also is not just a GPS satellite. It also contains a rocket launch detection system. Now, before the Gulf War happened, most of the military around the world said, we don't want something that is reliant on another nation's satellites. We want autonomous navigation. But when the Gulf War occurred, there were so many people who desperately needed, in that rather featureless terrain, positioning accuracy either for rendezvous or for general navigation. And mums and dads were putting little receivers into packages and sending them out to their troops, that it became much more acceptable by the military. And by the way, they turned off selective availability during the duration of the war. Now, if you remember this man, I don't think he was drunk then, but he was most of the time. He declared GLONASS to be operational in 1993. It clearly wasn't. Particularly the ground receivers, or the users' receivers, weren't really available. They had got quite a few satellites up there, but it wasn't really usable. However, GPS was declared initially operationally capable with some of those prototype satellites, together with the first of the production ones, in December of '93, and then a year and a half later, they declared it fully operationally capable because they now had enough production satellites airborne for 24, which was the expected number that would be required for global coverage. And there again, you can see the size of the later version of satellites getting a bit smaller. Now, what happened in Europe? Well, there was this resolution that came out which said, God, everybody's starting to use this kit in shipping, in aviation, cars, buses. We've really got to do something about it because we don't have any control over this. It's controlled by a military authority in another nation. We happen to be friends with them at the moment, but what happens if something happens in the relationship we have with America? So they decided that they would have to have some sort of confirmation service of how well it was working, particularly for aviation. So the European Geostationary Overlay Service, EGNOS, dreadful title, they started that program. What that consists of are a couple of geostationary satellites, satellites that sit on the equator, just like the things that produce sky, but they sit on the equator. They're fundamentally communication satellites, but what they do is they transmit down to people who are using GPS, who have got a receiver capable of doing this. They transmit down integrity data, which tells you what satellites are starting to go wrong or have a problem, and corrections, differential corrections. So again, selective availability was going to be wiped out by this. And by the way, there are now several hundred airports throughout Europe who are using EGNOS for not total precision landing, but down to 200 feet. Now they did finally get 24 satellites airborne for the Glonass system with one spare. But it didn't last long because their satellites, for whatever reason, although they had a design life of 5 years, very, very few of them achieved 5 years. The American Block II satellites had a design life of 7 years. Some of them have lasted 20. So this is the problem. They launched 3 at a time from a Proton M, and from 1998 until 2006, this is the decline of the Soviet Union, they were only making 1 launch a year at most. So, as you can see, from that original operational capability of 26 satellites, they rapidly dropped away. Well, this is unusable. No, this is not a constellation. Now, they started to build it back up again in 2001, which you'll see they declared they were going to get it back up to operational capability, and they poured some money at it, including some new satellites, which I'll talk about in a moment. And they have got it back just to 24. They're only just about holding their own at 24. And this was how they did it in terms of the life expectancy of a satellite. This was their new satellite, Glonass M, and it was predicted to have a life of 7 years. Well, some of them have made 7, some of them haven't. It's not been that good a satellite, to be honest. And they're already on to a Glonass K, and they're designing a Glonass KM to replace that. So what is GNSS, the Global Navigation Satellite Service System? Well, it's these two primarily at the moment, but it's also a lot of other augmentation systems. Space-based augmentations like EGNOS, and by the way, that's very similar to a system that's in America called WAS, Wide Area Augmentation, and in Japan called EMSAS. It's called EMSAS because that's the geostationary satellite in Japan that provides the service. And then there's a lot of other ground-based augmentations. There's a LUS system, as it's called. These are special pseudo-lights. They're like a satellite transmitter on the ground near an airfield that perhaps can give a better capability to do a landing. And a lot of the marine beacons around the world, controlled by the lighthouse authorities, have put in a differential service which transmits on the old MF beacons that lighthouses. Now, some of you may have heard of LORAN, long-range air navigation system. Well, there's an ELARAN available now, much more updated system, and it actually can carry on that 100 kilohertz signal the same information. It can carry correction data and integrity data. So that's now available in Europe, and the Americans, having turned all their LARAN transmitters off, are now seriously thinking of converting them all to this ELARAN standard and putting it back on again because of the vulnerability of GPS in general terms. I'll come back to that. Now, presidential directives don't come out very often, but this one was quite important in 1996. Firstly, they said, we will continue to provide that basic service worldwide, free of charge, to anybody who wants to use it, and we'll discontinue selective availability by 2006, because we know it doesn't work, because you've all got rounded by using differential systems. Now, in practice, they actually turned it off in the year 2000, as I'll show you in a moment. They started, because they wanted to be able to jam the civil signal, they started what they called the Navstar program. In other words, they were now going to produce a whole set of new military signals from the same, not the same satellites, but from new satellites, that they could jam the civil signals and leave the military alone for themselves to use, and their NATO friends, of course. They also went over to a big joint management system. Rather than just the military, they recognized that it wasn't just defense, transport, state, and commerce all had great interest in what this system was doing. And it's since been joined by Homeland Security, by the way. So this was the beginning, really, of what we now call GPS modernisation. Now you're about to hear probably the most daft comment that anybody's ever made in that year.
We have ignition and liftoff from Cape Canaveral Air Station of the Air Force Delta II launch vehicle carrying a new GPS 2R satellite. We have had an anomaly.
How she did that in such a calm voice, I don't know. Yes.
Once again, we had liftoff of Delta II launch vehicle from Cape Canaveral Air Station, and we just had a problem with the vehicle on the pad.
In practice, fortunately, nobody was injured, but they did write off about 60 cars in the car park there. They did eventually get one of these away, and this was a later design. It was the replacement. Block IIR stands for replacement. A new satellite, lighter, better designs in it. And after some extensive testing, they got it operational, obviously, as I say. Normally, they spent 6 months testing them. Now, this guy came out with the announcement that, having started the Navstar program, we'll add a special extra civil frequency for civilians to use, because we realise that just one frequency makes it more vulnerable, and we want the civilians to be helping to pay for this system apart from anything else. And he then promised an even a third system on L5, as it's called, in January of '99. Meanwhile, you might remember this fellow. He was the Commissioner for Transport in the European Commission at the time. He signed these two papers. I don't think he probably read them because he wouldn't have understood them probably, but they were worrying in Europe. They started this EGNOS program, as I said, and they were worrying in Europe that we were still reliant on someone else's bit of kit. And shouldn't Europe have its own system? And that was the beginnings, really, of what we now call Galileo. Oh, now I talked about removal of selective availability. That's what happened on the 2nd of May in the year 2000, as they said that would be the first year they considered turning it off. They did turn it off, because obviously it wasn't having the effect they wanted. It was felt at the time, because this happened at a European navigation conference in Edinburgh. The guy from NASA came and announced this on the 2nd of May, that it had just been turned off overnight. I'm afraid all the delegates there from Europe thought this was a cynical move by the Americans to try to stop, or at least interfere with, the Galileo program. Now, you see over there, we got down to about 20 meters. That's slightly improved since. mainly because they're getting the ephemeris data better. When I talked about the uploads of the ephemeris data, it goes into the satellite, yes, but it's predicted inevitably. So what you're getting on your little receiver is a predicted orbit from tracking of the satellites over the last few days. It's inevitably not as accurate as you could get, and so a lot of surveying use of GPS doesn't process the data on the day. They store it when they go out and do their surveys, and they wait for the more accurate actual orbits from yesterday and to process the data. So they get even better accuracy, but I'll come back to that. But it has improved anyway. Now, Galileo had a bit of a problem. You know, this came out of the summit meeting which said, we want to do this. But they kept on arguing. They kept on arguing about how it was going to be financed and the management structure. They didn't like the management structure that was proposed. And this went on for 3, nearly 4 years, before finally they agreed to fund it into full development. Fun enough, having agreed in the European Commission to do so, the European Space Agency, who were going to develop and launch it, started arguing because 2 nations, Germany and France, or 3 nations, Germany, France and Italy, wanted more of a say, and so they were trying to put more money into the program than they were being asked to put in. And ESA's projects can't work on the basis of being over-financed. As it happens, of course, it's been cost overrun, so it didn't matter. But that held up the final ESA program by about another 6 months. Now, having seen that this was going to happen, the US said, okay, come and talk to us then. And so there was a long series of meetings over about 18 months. And they came up with some agreements on signal structures. No signal by Galileo, no signal by GPS should interfere with the other system. And more importantly, that it should be interoperable. Similar structures of the signals and similar capability in a receiver to be able to use both. And non-discrimination. In other words, if Americans would like to bid into part of the system, why shouldn't they? I don't think they have, but not one anyway. But it meant that, that there would be open bidding between the 2 nations, and unrestricted access to those open services. Now, what they needed to do now in the Galileo program was get up a couple of satellites in order to prove the frequencies were being transmitted, so that the ITU would say, okay, Galileo has these frequencies in these structures, in that part of the spectrum in the L-band that these systems work under. They also wanted to put up some critical payload aspects like the clock and 1 or 2 other bits and pieces. Because this is not a very favorable orbital area, the medium Earth orbit, 20,000 kilometers, is quite a bad radiation environment. And the Americans wouldn't tell them anything about it, despite the fact they'd had satellites in that area for a long time. So the Galileo people said, well, we'd better put up some of our own kit to try and find out just how much hardening we've got to put in the future satellites. They launched their first one. It was actually built by Surrey University, that Giove company, Surrey Satellites, built the first one. And if this works, you'll see it go up. I like big rockets. Now, the satellite was nothing like the final versions. It was actually a satellite that the Surrey Satellite Company had already produced, and they just put into it the bits and pieces that would transmit the right frequencies and the odd clock and other detection systems. Nothing like the final production satellites are now, but at least they got it up there. It was transmitting within days, and the ITU gave a tick in the box to say, those are now Galileo frequencies, and we've given them to you. And I thought you'd like to see what's going on in the applications world, because this is the bit that dear old Brad Parkinson couldn't believe. He said he thought it was just a force multiplier, and it's gone berserk. Clearly the military everything from the drones to shipping, and soldiers have got them on their backs. Buses are using them in London. You might see the odd bus going around with GPS working. Truckers particularly are using them. Railways are starting to use them, but of course the overhead cables are a bit of an issue. It can cause problems. The biggest users, of course, are folks with these things in their cars. There's now, as they claim, more than half of the cars in the nation have got this sort of kit on board, either built in or one you bought from Amazon or wherever. The yachties have been using it for a long time, and high-speed ferries and merchant marine now because of ECDIS. I'm sorry if people don't know what that is. The electronic chart information and display system is now mandatory on ships over a certain size under IMO regulations. Those systems, which are digital mapped, basically, some have still some raster mapping from older areas that haven't been resurveyed, but most of them now are using digital mapping, and they are all driven by GPS, which makes them a bit more vulnerable than most. Aviation, of course, down to what I was saying earlier, you can now go down to 200 feet on lots of airfields. Procedures have to be developed for all of these airfields, but that's been done very well now throughout America and Europe. And of course, mountaineers are using them, hill walkers, and this was a University of Nottingham attempt to see how well we could guide a visually impaired guy. He got a rather large map. He actually got a laptop in his thing on the back here, which was speaking to him and telling him how to go to the post office and how to get to the train station from his current position. It was a sort of electronic guide dog, if you like. And other people have now taken it further. What amazes me is the guys I play golf with are forever telling me I'm 141 metres from the hole. I don't really want to know. Well, you know, that could be a 7-iron, a 6-iron, who knows? I just hit the ball. There is an emergency services requirement, of course, within Galileo particularly, but GPS is being used at the moment by all of these guys, particularly ambulances. I hope you've got your ambulance, position at home written down somewhere so you can tell the ambulance people precisely where to come to, because postcodes don't always work, but if you look on this, in the mode where it shows you where the satellites are, it will tell you the lat and long. And of course, engineering applications, particularly, for instance, this guy. He's got an aerial on each end of that dozer, and that now can be totally automated to grade the ground and exactly the angle you require. Now, that's not using the normal civil frequencies. And most of these applications I'm looking at here are not using the normal type of use of GPS that is in your TomTom or your Garmin. What they have done and developed over the years is using the actual waveform, the frequency waveform of the L-band transmissions, and measuring the cycle, part of the cycle that you're in. Now it means that when you start, you must know where you are, and you do that by standing still for a reasonable length of time, a few minutes. Having got a precise value of the signals you're receiving at the moment, you then move. And as long as you don't lose a cycle and get what's called a cycle slip, then you will maintain very high accuracy, down to centimetres and less. You do need to go lower than that, some rather odd corrections. For instance, we're going up and down by about 5 or 6 centimetres a day here, earth tide movements. Down in Cornwall, they get sea loading as well, and Cornwall goes up and down by even more. So they need those sort of corrections depending on where the moon is and the effect on these oceans and the earth. This Humber Bridge, this is, by the way, they asked if Nottingham would look at giving them early warning of any signs of structural failure in the cables of the suspension system of the bridge. So we instrumented it, we've put them on permanently now. That was a trial program that the university did first with tripods, but they've now got permanent fixed receivers on, transmitting back through the GSM system into Nottingham's office that I used to work at. And they are watching for any unusual changes in the motion of the bridge. So the bridge authorities will say, we've got a particularly heavy load going over at such and such a time, you should see some strange anomalies then. And so the guys will watch for it and see it go over, or if there are high winds. But more interestingly, they are now relying on these systems to tell them that there's something wrong. Something has moved more than it should have done. And that saves them doing so much more. They used to have to do visual inspections on all the cable works at regular intervals. They now know, and they've got confidence in the fact that this system will tell them that there's been an unusual movement in part of the bridge. This one was the old bouncing bridge, do you remember? I'm from the old military where they said, break step when you go over a bridge. Well, for whatever reason, all those folks who were going over to the museum or the art gallery the other side didn't break step, did they? And the thing was bouncing like hell. So they called us in from Nottingham to instrument the bridge for them so that they could work out the damping capabilities they would need to stop that happening. And so we were involved in that program back at the Millennium Bridge. Well, here's some things that you perhaps weren't aware of. One of the corrections we have to apply, because we're looking for millimeters errors, is how much does the water vapor in the atmosphere delay the signal that's coming through the atmosphere? Now initially we had to do this with a very expensive piece of kit which measured what the water vapor was at the moment above us. Met Office, of course, let off a whole load of balloons from 5 or 6 sites around the country to do this every so many hours. So they said, you think you can actually predict this? So we went into a program where we started working on how well we could predict from what we had now been working on for several years, how much water vapor was in the atmosphere. It mainly required that better prediction of the orbits. That was the biggest problem. And so we didn't use the orbital data that the satellites were sending us. We actually predicted it from our own measurements and said, yes, we can do it for you. And they actually handed over a large sum of money, and they now use, they haven't given up on their radio son balloons, but they actually are now using this data from a number of receivers around the country. Sea level rise, of course, if you look here, you can see there's a GPS antenna next to this sea level gauge, because Scotland's going up a bit and the southeast of England's going down a bit by several centimetres a year. So it isn't just sea level rise, it's actually the land going down as well. And coastal dynamics, we've got a big program out in the Mediterranean particularly, working with the universities in those nations, Jordan, a lot of other Middle Eastern nations, where while we can't say there's going to be an earthquake tomorrow, what we can say is that we are seeing stress across part of where two of the parts of the crust are separated in fault lines, and we can say it's likely, and it's getting more likely because that stress is getting worse every month that we look at it. Now these are probably less obvious applications. Timing synchronization. These things, as I say, are high accuracy atomic clocks in space. They're corrected regularly from UTC on the ground, and so power distribution is controlled that way. Your mobile phone system only works because it's a TDMA type system. It only works because the cellnet systems are using GPS timing. And a lot of financial transactions rely on highly accurate, within a few nanoseconds of timing. Agriculture. This is a field near me. Okay, this guy isn't selling anything, but on other occasions I've seen him using GPS, that's his antenna on his tractor. They now look at the crop they receive, or the quality of the crop that they get from different parts of the field, so they can apply more fertilizer to areas that are not as good next year. These guys over here are actually in Wales. Chernobyl, the outcome of Chernobyl is still affecting some of the land in North Wales. So these guys have got a GPS receiver on their backs and they're monitoring how much radiation they're taking in from the grass, and we just track where they are for them. Animal navigation, of course, not only pigeons, but all sorts of animals now are tracked using GPS. That's the size of a typical chipset now. In fact, the latest one, which has Galileo and Glonass in it as well, that I've seen, is even smaller. So, modernisation, back to that. Well, they wanted this Navstar program to get going, yet they'd already built a whole bunch of these Block IIR satellites. So they said, okay, 8 of them we will modify to produce these military signals. So they started that and launched the first one, and 8 of those have been put up to meet that 1996 presidential directive. They launched all 7 of them, but one, or 8 of them altogether, but one of them has had a problem. The L5 frequency on that particular satellite affected something in the satellite's power supply, and they've had to shut it down. They also wanted to go on. They'd already started another program called Block 2F, which was just an interim program, but they wanted to go to GPS Block 3. And so they awarded a contract nearly 10 years ago now to Lockheed Martin to look at GPS 3. But they also had some funding problems. The Senate Armed Forces Committee and other elements of the financial side of the American government say you can have 24 satellites up there and some spares, but that's it. So if they're still working, don't put any new ones up until something fails. Well, as I said, many of them have lasted 3 times their design life. So it's become an embarrassment that they can't modernise the constellation as quickly as they would have liked because the systems were too reliable. Now they wanted to launch one of these Block 2Fs and it kept on being put back, partly because they couldn't prove that the thing was working properly, but also because there was funding issues. But they finally launched one on the Delta IV, and they've now built 12 of them, and 10 of them are now in orbit. They transmit the same signals as the Block IIRM, in other words, the civil signals that we expected, that we've always had, plus this new civil signal on the 2nd frequency, and the one on L5, and also the military signals, the ones that they will still be able to retain, even though they will jam the civilian ones. They're looking at the Block 3, they've now got 8 of them on contract, and these are supposed to have a 15-year design life, and they expected to launch them, as you can see, every year, and they're now talking about maybe 2016, they'll perhaps come back a year again. The reason why it's been held up is, in order to do that and use this new one, they need to bring up to date the ground control system, because the new satellites are much more complex in the way in which they operate, and they need therefore to have a modernised ground control system. And that had problems when they first went through the design reviews. It got delayed quite badly, and that's delayed the launch of the satellites. It doesn't matter because they've still got the old Block 2F to put up. Now Glonass has gone through a similar program of updating. They said, as I said, that they were going to double their spending. They planned to get 24 satellites by 2010. Well, they got close. And they launched a whole load in this period, as you can see here. But the last launch failed dramatically as it went into orbit, and all 3 satellites fell in the Pacific. So they were put back a bit by that. They are going through a new, they were Glonass M's, they are also going through a Glonass K update, and the first one of those has got a CDMA signal on. In other words, they're recognising that they ought to be more interoperable with GPS and Galileo in the future. So they are now putting a code on their signals, not relying totally on frequency to distinguish between satellites. They launched one in February. They were planning to launch another one, but after that triple loss, they decided to put it off for a bit. And they've gone through single launches for a while, using Soyuz. Then they did a Proton launch with 3, and then they had another, they actually got 24 satellites up there, first time in 15 years. And they launched yet one more, and then sadly, this lot fell on the pan. So they lost 3 more. The boss of whatever it's called, the Russian Federation rocket system, got the sack, and obviously they've had a big review of reliability of their launching systems, before they continue. So they've had some problems. They've gone back to single launches on Soyuz. Galileo, well, they did launch what was a genuine prototype, not that Giove satellite one, but a more practical satellite. And the next two launches were to insert 4 prototypes for in-orbit validation. They did that. They were launched in 2011 and 12, and they produced good fixes when all 4 were in view. Same problem. You've got to see the satellites to be able to get a fix. They're still working, but one of them, for whatever reason, is now only transmitting on one frequency instead of all of the frequencies. Because Galileo transmits on about 5 frequencies. Now, the first 2 were launched in August last year, but they ended up in the wrong orbit because of a failure in the frigate upper stage of the Soyuz rocket. Since then, with a lot of good work by folks in Europe, they have actually managed to correct the orbits closer to circular. You still can't get them perfectly circular, and they've used a lot of the fuel of the satellite to do what they've done. But at least it means they won't be totally wasted. They will be usable when they turn them on for operational use. They've got 2 further double launches that have occurred in March and just one just the other day in September. The next double launch is due in December on the Soyuz, and then they're going to start using Ariane 5 to launch up to 4 at a time. That's going to be a bit of a gamble. Having watched what's happened to the Russian launches with Proton, it's a bit of a gamble, but they feel they've got to get there because, as you'll see in a moment, the Chinese are rushing up behind us. So in 2017, there should be 2 launches, Soyuz with 2 satellites and Ariane with another 4, trying to get to 24 plus reserves, up to 30 satellites in orbit. So when will they get this operational? Well, they said 2008 initially when the program started. It keeps going back. They're now saying 2020. So what's been happening elsewhere? I'm sorry, Galileo is going to be pretty interoperable. You will be able to buy a Garmin or a TomTom that will receive both. You say, well, it works perfectly well with GPS. Well, it doesn't work too well. You don't know it. But if you go into an urban canyon or under trees, what it's doing is locking to the road you're on. It's using the map because it's lost sight of the satellites. It isn't until you come out the far end that it goes back to working properly. With more satellites in view, it will maintain better lock throughout those areas where you go into a blanked area. Now the Japanese wanted a regional system. They said, how can we best attain this? Well, they were using their MSAS, which was their equivalent of wide area type augmentation system, but they wanted to go to what they're calling an intermediate geostationary orbit, which is one that, yes, it stays relative to the equator in the same place, but it does an orbit like so. It's going down fast when it's down here, but over Japan it's going slowly, and so it's in view in the vertical for far longer. And that's one of the problems. GPS, the satellites come over the horizon, they go wallop, and a few minutes later they're off the other side. It's good if you've got some above you. The reason for that is the fact that you've got lots around you means you're getting pretty good cancellation of any errors because you've got lots of positions from 5 or 6 satellites on the horizon or just above. But your height isn't as good because there aren't any satellites below you. But if you've got more immediately above, you're going to get a better error, reduced error. So that's what they were after here, and they've started launching this system, and they have said it usable, and it's in use now as a regional system. It's not even trying to be a global system. In India, they've also introduced, and it's not yet operational as far as, no, they declared it, sorry, I didn't think they had declared it yet. This is similar to EGNOS for India. So it's an augmentation system. It's not adding anything other than correction and integrity data. Yes, all the GPS satellites we're seeing are working correctly. And they plan to have it work with Galileo as well when the time comes. They, however, want to go to a proper regional system of their own, and this is what they're starting to do. They're going to launch 3 geostationary satellites and 4 of these intermediate ones to be a regional system over India. So, yes, BNO1, this is the one I talked about earlier. It's a transponder system, so it's limited to the number of users that can actually access it. So that has gone out of use. They've decided that is not the way forward. And they're going over to BNO2. And this is their plan at the moment. They've got 3 of these intermediate geostationary orbits up, 5 geostationaries and 7 medium Earth orbits. They intend in the end to have something that's looking very like GPS and Galileo, except we are launching specific geostationary orbits. We've got other communication satellites that can do that job, but they are actually making part of their program. So where are we at the moment? What's the status as at yesterday? Well, here's GPS, as I said, 32 up there because some of those that are up there are extremely old. They're down to the 1 clock or the 1 power supply, and so they're saying they could fail any time, and they've persuaded Congress they've got to have some spares. In fact, as you can see, really about 8 spares. 31 of them are operational. 1 is in maintenance. That's the one actually that failed, but they've left it there because they're still hoping they'll get it to work in the long term. And here's the mixture along the bottom. Some of the very old ones, 2 of the old Block 2As, they're getting up to 20 odd years old now. And 10 of the 2Fs, the latest ones. And there's 2 more of those to launch. Here's Glonass, 28 up there, 24 are operational at the moment. 2 under check by the contractor. That usually means they ain't going to work again. And they've got 2 of their latest ones, the K models, up there, which they haven't yet released. I said when most of these people put up a new satellite, they test its transmissions for about 6 months before they switch it on. So, is it the perfect solution? Well, it don't work in tunnels, obviously doesn't work indoors, and a lot of people want to know where they are indoors, and a lot of people want to know where you are indoors. In other words, they want to tell you as you walk past the rack with the latest wine offers in Tesco's, that, oh, there's an offer on your phone. God damn it, I get enough phone calls to do. Urban canyons, as I said, are a problem. Trees are a problem, and these sort of bridges are a problem. So there are constraints to the way these systems work, and Galileo is going to be no better from that point of view. They're also vulnerable. They're very easy to jam. If you look on the internet, you can find how to build yourself a jammer. And it doesn't take much of a jammer to jam this system. It's a little light bulb, really, in space, the power of it. So it doesn't take much. There's a little bit of gain on the signal-to-noise ratio because it's coded, but it still can be jammed very easily. It's also reasonably easy to transmit false GPS-like signals. There's a guy who's made a bit of a campaign of this in America, driving around in his truck with a laptop on his knee, actually producing look-alike GPS signals and buggering up the taxis that are around him. And although it's rare, GPS receivers do fail. They're pretty reliable bits of kit. The one that was a spectacular failure was on a cruise ship called the Royal Majesty, which came out of the Bahamas and was going up to Nantucket. And I'm afraid somebody went on the roof of the bridge and accidentally kicked the aerial connection between the GPS and the receiver in the bridge. They went through 6 box changes and didn't notice that the GPS was in DR mode, feeding directly into the autopilot. And they ran aground. Didn't hurt anybody, but it was £500,000 or £1 million worth of damage done to the ship. So, if your life depends on it, carry a spare receiver and always have a backup. Okay, take a map with you for goodness sake. Now, these are some of the potential backups. Obviously, the aviation world has got inertial navigation systems as a ring laser gyro. Pseudolights, but they're going out of favour because they're bothered that the power of them might be a problem to the use of the power level that you're trying to receive from space. Map matching, as I said, these things, if it starts to lose signal, it'll lock to the map. And you won't know that for quite a few seconds at least. There are terrestrial systems, obviously. Even the phone system can be used to position you. There are some systems now that assume you're at the base station that you're receiving your signal from. Now that's okay in the middle of Manchester because those base stations are behind just about every other advertising board throughout the city. So you're never going to be more than probably 100 metres from one of those. But out in the countryside, where I've just come across the Pennines, you could be 2 or 3 kilometres from that base station, so not a lot of use. Loran, however, is coming back into its own. It was ignored by the latest regime when they took over in America, and they shut them all down as Grandad's system that was out of date. But they're now having second thoughts, and Europe has already said that they're going to continue using Loran, mainly for marine. Now, you can't blame the sat-nav for that. That was the mapping system that he got, because what did he got? He got a 70 quid Garmin, hadn't he? And it said, this is the way to wherever you want to go. What he needed was an advanced TomTom system, which cost him 350 quid. But that would have been cheaper than having a crane to get him out of there. In fact, I believe Mercedes have got so fed up with it in terms of their trucks being in bad odour because they got stuck in places like this. They're now insisting you can't buy a Mercedes truck without a GPS system in it that has the weight and size of the vehicle in the mapping system, so you don't end up in that situation. So, what I can say is, watch this space, it's still not going to happen.
Okay, I guess you're all dying to ask a question, but I shall give you a warning first. We're filming this tonight, so if you've told your wife you're with your mistress, or that you slipped down the pub, and really you're here feeling guilty, you may yet see yourself on film. So with that warning, and with the lights coming on, I'll throw the floor open. But Norman, I'm itching to ask the first question. So the first question I'd like to ask, someone in this audience taught me, Derek, I think you're here, Derek taught me the Earth isn't round. How do the satellite navigation systems compensate for that?
Okay. Well, some of you may have heard of something called WGS-84. The World Geodetic System. There was one in '72, but GPS wasn't actually up and running then. But by 1984, when they had a big survey of the world and the Earth's shape, they decided that that was what they would adopt for GPS. So the GPS would work against that parameter. Inevitably, most of the mapping of the world is not, or wasn't then, on WGS-84. So there are lots of errors between our datums that we use in the United Kingdom, the European datum, the American datum, and WGS-84. And that particularly hurt folks like mariners and aviators who had lots of their data in the old mapping system. Ordnance Survey very rapidly picked this up and they started converting all their charts to the WGS-84 and its successors, because it's gone on from then. We still talk about WGS-84, but it's now really the ITRF, the International Terrestrial Reference Frame, which is updated regularly. And it's not just the shape of the Earth, it's a gravity field as well. Sorry, move on from that. And the Hydrographic Office did the same thing in this country. They started updating all their charts, and before they updated them, they put corrections between the old datum and GPS, so that anybody using them could put that in as an offset as they approached a harbour. Aviators were obviously even more worried, because a lot of the beacons around the world that they were still using for routing in those days were on whatever local datum it was, and they've all had to be resurveyed into the new International Reference Frame system, particularly for ICAO, for this future navigation system that they wanted to adopt. So yes, that reference frame is very important. It's the closest that you can get, with reason, to the knobbly shape of the Earth. The gravity fields are particularly important though for orbital data as well as the charting and mapping part of it. So this actually has in it that reference frame, and that's what it is using when it calculates your position.
So the satellites know that the Earth isn't round, obviously.
Well, yeah, they are being updated on a regular basis because there's a relativity issue in this as well, but don't get me into that. They are updated on a regular basis of what the gravity field is in terms of their orbital parameters, yes. Oh, we're talking several, I should have said, in some cases around the UK, it was a couple hundred metres difference between the local datum and what was in GPS.
And how often is this update going on? Is it
It's
weekly?
Oh no! It's
Yearly?
I think it's annual, because we're talking now very small changes. Having got to a datum and produced a pretty good. The '84 version wasn't bad, and they've only tweaked it really annually since then.
Gentleman, the second.
Well, what happens with driverless cars when somebody switches the signal off?
Well, they hit a wall, I would think.
Can I reply to the input?
Yeah, but GPS isn't the only thing they're planning for those. There's lots of laser systems and CCTV systems built into them as well. In fact, there's one at MIT in Cambridge that I've actually been in. It doesn't look much like a car because it's got more air wheels and cameras on the top. But it worked. They took it round a series of roads with a driver there just in case. But they showed that it worked fairly well. I was more bothered about what other people might do cutting you up. Would the system react quickly enough? It did seem to, but there were a few jerks.
The gentleman in the middle and then...
I'm sure I'm not the only one to have noticed this, but if you're driving along in the car, looking at the speed of your car on the sat nav and the speed of your car on the speedo, there's a discrepancy.
Yes.
The car...
There has to be. It's it's not only British legislation, it's European legislation that your speedo must never overread. Sorry, underread. Underread. So you will always, because of tyre wear, have your speedo slightly overreading what GPS says.
So the satellite's more
Absolutely.
accurate than the car.
Oh yeah, more accurate than the car. Because obviously, if that otherwise, the car manufacturer would be. I think it must be 10%, between 5 and 10% less than in reality. Because otherwise, the car manufacturer would be the person you would go and claim from to pay your fine.
Right. My mobile phone says it can use GPS and the Russian system.
Yes.
Can it do those at the same time, or does it have to switch from one to the other? Are
No.
they on different frequencies, or?
They are on different frequencies, but it is almost certainly using it at the same time.
So they can use all the satellites, both the GPS and the Russian ones?
Yes, if
to
they're,
help to
whatever's
fix
there, it will attempt to use. The GLONASS system is not quite as accurate as GPS, but it's not bad. It's where GPS is claimed now at 8 to 10 metres. GLONASS is probably more like 15 to 20 metres, but that's pretty good.
But you've got more satellites to choose from?
Yes, and that's why we're so keen to get Galileo available, because who trusts Putin at the moment? You might deliberately bugger it up. In fact, it's had a couple of big issues recently. They turned them all off for a couple of days recently because of some error in the uploads they'd done of the ephemeris data, and they were producing large errors. So they turned the whole system off for a couple of days. So it's not been as reliable as it should be, GLONASS. But yes, if it's there and the system says they're working, it will attempt to use them. Yeah, absolutely. What you may also have, depends which smartphone you've got. One of the things I mentioned was this ephemeris data. You need the navigation message to tell you what the orbital parameters of the satellites are at the moment. They're predicted, as I said, but they're vital to your ability then to measure position. Now, it's quite a slow bit rate to get that, which is why if you haven't turned your GPS on for a day or two, it takes a little longer to actually hackle, okay, and start working. Or if you go into a building and come out again, sometimes you'll see it will take a little while to come back on again. Or what is now available on a lot of phones is something called assisted GPS.
Oh, yeah.
What's happening?
Where they use the mobile phone.
What's happening is the GSM stations have GPS receivers in them because they need the timing capability to synchronize your phone and make the blooming things work at all. I leave mine turned off most of the time. That now can transmit to you much more quickly if you just turn it on and you've got the
To give you a
phone with
rough
that
position,
capability.
yes.
You'll get a much quicker light up
Yes.
of GPS positioning because it can get the nav data from the phone system and doesn't have to wait for the satellites. That's called assisted GPS. Quite a few phones now have that built in. It does inevitably mean that your phone battery will run out a lot quicker.
Gentleman here in the second row.
If I go on to Greenwich and stand on the line which is marked on the concrete,
Yeah.
which you've all seen,
Yeah.
presumably
It's not quite WGS 84.
Is it zero by definition still?
No. No, WGS 84 is slightly different. It's marginal, it's a few feet, but it is not on the meridian anymore.
So
Not quite.
what is now defined as the zero?
Well, it's still called the Greenwich Meridian, it's just not that line that's at Greenwich.
The longitude origin
Yeah.
is a matter of definition.
Yes, that is still, it's still called Greenwich, and it's still part of the system. It's a bit like we still call it Greenwich Mean Time. It's Universal Time Coordinated, UTC,
Yeah.
which is not.
But that is corrected periodically, so that the difference hardly matters.
Oh my God, you're going to get me into leap seconds now, aren't you? Ah, here we go. Yes, okay. The GPS guys are making a big fuss about leap seconds because it causes them some trouble. These things have what's called GPS time. Okay, on there it says UTC. If you switch it on, no question, it's correct. But to produce that, it's had to have added the number of leap seconds onto its GPS time, and that's, I think, 33 different now. The poor old Earth was defined, or at least, sorry, the cesium standard of time was defined as the tropical year 1900. A pretty stupid year to have chosen, to be honest. Because since then the Earth has slowed down a bit. We won't notice it, we won't fall off it, but it is slowing down a bit. It's actually reduced now. It was slowing down quite rapidly in the 50s and 60s, but it's slowed down a bit. We were getting a leap second about every 18 months. It's now about every 3.5 years. And that's because to keep the blasted, what's the word I want, scientific clocks in line with what the Earth is actually doing and when the sun comes up, you've got to have leap seconds because they've defined it because of that year, 1900, and we're stuck with it. And these guys moan because they have to change the software in the systems and transmit it to satellites every time it happens, so you read UTC on here. But in practice, they work in GPS time. And that's another problem. Galileo has set the same thing. They've set Galileo time. It's not the same as GPS time. So it also, the satellites also, and that's what the Americans have agreed to do as well, it will also transmit the difference between GPS and Galileo time when Galileo goes fully operational. But time is the essence. That's why this system works.
Every so often you get a terrific electromagnetic surge from the sun.
Yeah.
How do they cover that?
Yeah, coronal mass ejection we're talking about. Mainly related to the sunspot cycle, the 11-year cycle, which the last one wasn't as bad as the one before it. Of late, the maximum of those big surges has been reducing, fortunately, because there were some bad issues. I think Canada had a major problem with synchronization of their electrical grids because they had a coronal mass ejection that hit their area particularly badly, and it blew away the timing on their electrical grids. Fortunately, that hasn't been as big an issue of late as it was 5 or 6 years ago in the last sunspot cycle. And we're just on the decline again now. We've just had a maximum, so we're working away from it for another 5 or 6 years before we'll hit a maximum again. But it does affect the satellites, no question. there's also another effect to do with the, on the equator. You get some, in Brazil and areas in South America have had some quite nasty effects where they've had large errors due to a build-up of ionization from the sun. And for some reason it affected the equatorial areas more than it affected temperate areas.
Brian, you're the astronomer here, so
yes, I was speaking to a professor of astronomy a couple of weeks ago about the law of the minimum. This is the, another 300-year cycle. Last one taking place 1645, 1715, where the sunspot activity declines to zero for many years. And there is now evidence that the law of the minimum, in fact, will come again. We're thinking sometime in the 2020-2030s that we will actually see a complete decline in sunspot activity. And that is recent data, I think, from
will this lead us to an air of false sense of security if we don't have such incidents?
You can worry about it in 300 years.
Yes, sorry, go on.
Timing is obviously extremely critical in this system. I was told that you actually have to take into it, because of the speed of the satellite, you have to take into relativistic effects in order to keep the timing correct.
There is a correction. The satellites actually transmit slightly, you know, they have a correction in them that applies because of relativity. Yes, they do.
Gentleman in the third row, and then
I've got a Garmin GPS, and there are certain locations in the country, whenever I pass through them, it turns itself off. one of those locations was near Menith Hill, and I wondered whether it was a military specification that it should be turned off.
No, not heard of that one. But the military got into a lot of trouble about 15 years ago. They wanted to, you know, we need to know whether GPS can be jammed easily because we're now using it in bombs and all sorts of things. So we need to know, and in our drones, whatever. So they started doing some trials. Well, there was uproar because, of course, it affected the fishermen and the government, the oil industry. So although they put out a notice to airmen, which said we're going to jam this, they were then told, no, you turn it off immediately, and they had to stop. Also, the Trinity House guys have done some trials off Spurn Head in one of their, their ships that they use for checking buoys and things in the ocean. And using an onboard jammer, they blew away their navigation system completely, and they were only transmitting 2 watts. So it's, it is quite worrying. It is extremely vulnerable to jamming. And as I say, you can actually buy a GPS jammer if you feel like it to plug into your cigarette lighter on Amazon. You're not supposed to plug it into your cigarette lighter. It's not supposed to be switched on, but they can't stop you buying it.
there are no terrorists present, I hope.
But presumably this is the problem, the terrorist type activity, because presumably for the main countries, you've got a sort of mutually assured destruction situation, like with the atomic weapons, insofar as they know if they do something, they're likely to be hit just as badly.
Well, the only thing I can say is that too many people are relying on it now, including the terrorists. So, at the moment, fortunately, the only people who seem to be messing with it are either accidentally or perhaps deliberately the trucking industry. They don't want their bosses to know where they are. We were called on by one of the British gas companies. They wanted to do a trial of using GPS with mobile phones to track where their maintenance vehicles were. It was something about Birmingham, this one depot, they want to do it. So before we do anything though, we must check with the unions. So they went and talked with the unions, with us, and said, can we do this? Oh, yes. Well, your guys, we will know where you are, we will know if you're speeding. Yes, okay. They didn't ask for more money, amazingly. Anyway, they started this with, I think, about 10 trucks. And everybody, it worked a treat, in all except one, who they saw it start up in the morning, his van, because they took him home, these vans, and then they lost him until lunchtime. So, what's he doing? So they went to the union man again and said, can we talk to whatever his name was? We keep losing him at lunchtime. Oh, until lunchtime. Oh, yes, well, all right, well, I'll come with you. So they went to see this guy, and my professor went with them, and they said, you know, we're confused about why we lose you between starting up in the morning and lunchtime. What do you do in the morning? Oh, come and we'll get you more van, and look what my jobs are, and I drive up. Yeah, but what do you do? Oh, I don't do anything. And then they noticed some silver foil in the cab footwell. What's that? Oh, that's what my sandwiches are in. Where did you put them? There.
Further towards the back, yes.
I had a very interesting private lesson in the effects of relativity on navigation a few years ago. I went to the Einstein Museum there, and I was the last paying customer in, and the curator was rather keen to get me round and out again, because she apologised. She said to rush because we've got a private party coming in later. So she took me round and told me that the general relativity and the special relativity required opposite types of corrections for the navigation. Otherwise, you would end up with a cumulative error which was several nautical miles per day if you hadn't got that. She said Einstein would have been very interested if he was still alive, because I think he thought it was a bit of a theoretical thing with no great practical application, but clearly there it was. Because he was a sailor, that was his chief hobby. And so, because he sailed in Switzerland, Berlin, when he got to Princeton in the United States, and she told me he never learned to swim. So he obviously great faith in his own ability. It's worth going to if you're able to go.
I don't know if you've been reading the Star Wars thing where they think that if it was in reality, one person would be about 100 years older than the other person when they met, even though they were twins. Have you been reading that story? Sorry.
Yes, just a quick question about archaeology programs. You quite often see some sort of GPS device being carried around to plot positions. What are they doing to get precision?
Well, they're using what I call a real-time kinematic system. They're using this frequency and measuring part of a cycle. So they're getting down to centimetres or less. It takes more time. It's a surveying capability, really. In fact, the surveying department at Nottingham University I worked in used to help the archaeologists quite a lot. We used to send people with them on their field trips that they did to make sure that they understood the kit that we were helping them use, Leica equipment particularly. It isn't straightforward. You've got to understand.
Does it require them to put up a transmitter?
Usually, well, you don't have to now, but when we started doing it, you had to have one that you would put down as a static transmitter, and then you move the other one, and you would relate the two together by what's called double differencing. Now, there is such a huge network of Ordnance Survey reference stations, you don't need to do that anymore. You can use the Ordnance Survey network.
So the Ordnance Survey are transmitting?
Yes, they are. I think it's on the internet, to be honest. It's easy enough to get hold of anyway.
Derek?
Yes. I think this is probably an unfair question, but if you think about satellite television, to get a decent signal to noise ratio, you have to have a dish of maybe a couple of feet in diameter. Now, if you think of the average car trying to track GPS satellites with half a dozen tracking dishes on top, it would look a bit odd, to put it mildly. So, effectively, because the receiver has got such a tiny area, it must be receiving a signal which is many tens of decibels below the noise level. In which case, there must be some sort of integration.
Well,
I've thought very hard about how to do this.
It's the coding. It's the coding. Because you're looking for a satellite code transmission, it actually does improve the signal to noise ratio dramatically. Because you're looking for a specific code to match with one that's in here already.
How do you pick up where the pattern starts and stops? That's the bit I don't understand.
Well, There is a time tag on them, effectively. Every second there's a time tag that is giving you a new code start. And so that is how this thing works. It's getting that signal noise ratio by looking for a code.
Very quick. Does that actually, hello you, on this but does that actually amount to integrating the signal effectively? Because you're looking over a number of sequences. So is that effectively an integration?
Yes, in practice, yes, that's what you're doing. It is changing. Effectively, if you watch it, it's updating every second, which is one of the problems that in that code system, rather than the RTK system, is one of the problems. If you're in a fast-moving missile or an aircraft, every second isn't good enough, which is why they now regularly integrate the system with an IN system, which is probably working at 100 Hertz, so that the IN system carries you between the second intervals of effectively getting a fix from GPS. If you notice, if you can switch off the map matching, but I don't think many of these things let you, but the receivers I've used do, you can switch it off. And you turn a corner, you notice that the system tries to keep you going in a straight line for a bit, and then catches up and catches round the corner.
My sat nav does that because I bought it for 15 quid on eBay. It's wrong.
So it's probably not map matching.
Yes, it will keep you trying to go
Yeah,
straight and then
because it's effectively trying to produce a position every second, and so there isn't enough capability in it to understand what you're doing. That's why, in military terms, they integrate it all the time with an IN system, because the IN system fills the gap. It also beautifully trims the IN system. If you integrate it properly, you can update the IN system and gradually understand the errors of an IN system. You know, there's a major error of an IN system called shoe oscillation. Does that mean anything to anybody? There was a man called Schuler some years ago who theoretically said, if you had a pendulum the length of the Earth's radius, it would actually swing backwards and forwards with an 84-minute cycle. Well, that's exactly what an IN system does, because many of the correction terms to keep you on the surface of the Earth, going round corners and across meridians, the radius of the Earth is a factor in the correction systems. So in practice, if you start an IN system up, and don't move, just stay where you are, and if it has a little error, you'll notice it will swing backwards and forwards, just like a pendulum, at 84 minutes. Very precisely. It'll have inevitably a slightly exponential growth of error as well, probably, depending on how good an IN system it is. But that 84-minute cycle is prevalent. GPS allows you to correct that. What's even better now is that when I started flying with IN systems, I'll go back a bit, it took 20 minutes on the ground to align the damn thing. You know, you'd sit in this lovely high-speed fighter, you're going to go and catch some bear up off the Scottish coastline. You had to wait 20 minutes to align a blasted IN system. Because the gyros had to be warmed up, spun up, then had to look for the Earth rotation rate in order to get true north, and then leveled by the accelerometers, and then you were ready to go to navigate, and then you took off. Now, ring laser gyros, much quicker, because there's no spinning gyros in them. But what's more important is GPS, you can actually take off. Don't bother to align anything. Get airborne, get GPS, switch on your IN, and it will align the IN in flight. It has made a huge difference to the military. Really is.
Can I come in with another question on that? You spoke about satellite failures, but one thing that someone responsible for satellites told me is, whatever you do, you mustn't lose one. He was talking about the early days of satellites, when you had to do a calculation to make sure that you knew where it was in orbit so that you could send signals to it. But that presumably is...
I think they've got plenty of tracking stations now.
Oh, right. This was going heavy down, I guess.
One of the things they have done in America, when they first started, they had some tracking stations around the world because they got lots of friends in Australia and wherever else. We've got one or two for them. All around the world now, they've got tracking stations and upload stations. So GPS is now a thoroughly global system. That's one of the problems of Glonass. They've got many friends. Most of their reference stations are in the Eastern European countries or in Russia itself. That's why it's not as accurate, to be honest, because they can't track them well enough to keep the predicted data that they're sending out to them accurately enough. If they could get a few more friends, more humans, then maybe they could improve it. But at the moment, most of their tracking is in the Russian states themselves and nothing else outside. But I think we've got an agreement with India as well, but that's about it. Whereas the Americans got them all over the place, and Galileo is doing the same thing. We've got them all over the place.
Okay, well, talking of friends, we've got a dinner planned, so I'm going to wind things up now, unless anyone's bursting for a last question. Dinner is over at the Ox Noble if anyone wants to join us. But the main thing is to thank Air Commodore Norman Bonnar very warmly indeed for a truly excellent paper tonight. Norman, thank you very much. Before you go, 3 very quick reminders. Saturday the 3rd of October, Stevenson Locomotive Society